Like a Beza.
Wait, are you having like an interview?
No, no, this is
Why? Why? Oh,
there's reasons of laziness.
wow. Nice. I need to have that motivation.
Yeah, yeah, they do.
Yeah. Okay. Should I introduce myself? Whatever. Okay. You can. I've never done this. Sorry. Okay. Hi everyone. My name is Jennifer. A 1242 tutor. Um, I'm just gonna explain a little bit about op amps, just an introduction. So we know, as you see from the screen, this is how an op amp looks like how we draw it schematically, but in real life, it's like an integrated circuit. I don't know if a lot of you know about integrated circuits. So it looks like something like this, and then it has pins. It has different pins, and all these different pins have like there is power supply, and you know, and also like the outputs. So let's concentrate on the schematic, the schematic drawing. So in the schematic drawing, we have in the schematic, before I continue, so the main reasons for op amp just means an operational amplifier. So it can do a lot of operations like summation. It can also do multiplication, and also it can do um, it's not doing it. It is. Okay, I start again. Hello. Ooh, wow.
Nope, that's not the answer.
Hello. It's working. Okay. So should I start again?
I'm not hearing you. Like, if I'm in Zoom, right? Are you sure you guys can? I can't hear you.
I'm telling you right now, it can, her voice is coming through.
Oh,
Your voice is coming through. Hello? Yeah, we're good.
I'm not hearing you.
You don't need to hear.
Okay. Should I start again? Yeah, yeah, just go to. Okay, hello guys. My name is Jennifer, and I'm a IEEE tutor for 1242. I think a lot of you have seen me. I'm just gonna give like an introductory of an op amp. The full meaning of op is operational amplifier. Um, Operational amplifier. On this this side, we can see it's a schematic of an operational amplifier, but in real world, operational amplifiers comes as an integration circuit that has different types of pins that you have to like connect. So I'll just concentrate on the schematic. We can see in the schematic we have like the inverting input and non-inverting input. You should not like get confused with this too, because sometimes people get confused with that. So inverting input is on the negative, and then non-inverting input is on the positive. And then we have power rails. They're called power rails. So we have positive, the end, we have negative. So these ones are just the input. Like for example, the non-inverting and inverting, we can give it a signal, and either it can multiply it with a gain and we can get an output from it. Let me not go deep in that because you're going to learn that in your upper classes. Uh, I can just explain what operational amplifiers do for now a little bit. They do addition, subtraction, integration, and differential. And then we also have the golden rules for the operational amplifiers. So these golden rules, like the voltage one, comes because of a virtual short. I don't want to explain that so much. I'm just gonna give you like because I don't want you to get confused. And then the current comes because of the high impedance. So these golden rules, when you understand these golden rules, it's going to be easier for you to calculate and calculate the necessary prompts that they give you to get or walk through in the operational amplifier. So for example, we are given question 1. Assume that the voltage source Vs, that's an input, and it's on the, so operational amplifiers come in different ways. We have inverting, and we have non-inverting. We have summing. I think we have difference and different. The different. Okay, those are the ones that you learn from. Okay, so we have those that you're gonna be learning right now in 1202. And inverting just means that we provide a signal, a voltage signal to the negative input, and then the non-inverting, we provide the signal to the positive input. And then summing, knowing summing is I don't know, I just know how to draw it.
It's okay, they'll be good.
Okay, you're good. They'll go through it, and then differential also, they'll go through it so that you can understand how you can calculate it. But this one right now, as we look at it, we see it's a non-inverting amplifier, because we see that the signal is the signal input is at the non-inverting terminal. So here we are given Vs is 5 peak to peak, and then we have R1, which is this resistor, which is 1800 ohms, and then this resistor. So the resistor that is always connected to this resistor mostly is known as RF. So it's like most of the time you will see in your calculation they put RF. So most of it we just know it as that one. And then we have this resistor here, which is R3. So they say that find I1, I2, I3, and I out. Okay, so I1. So number 1, using our golden rules, we know that the current here is gonna be 0, and the current here is gonna be also 0, but the voltage here is gonna be as the same as the voltage here. Okay, so if we use KVL, sorry, is it KVL or KCL, sorry. If we use KCL, and we know that KCL is current inside a node is equals to current inside a node, the summation of current inside. So if a current is coming in a node and a current is coming out of a node, the summation should be 0. So here we see that in this node, there is a current coming in, right? And this current coming in this node is I1. And then the current coming in also this node is I2, right? Which equals to 0. Okay, so we take the current here. So we look at here. What is the voltage here? The voltage here is 0 because it's connected to the ground. So that is going to be 0 minus. The voltage here is going to be the same voltage here because of virtual short. So that is Vs over R. So that is I1. And then plus I2. So I2, the voltage here is the same as the one there, which is Vs minus. The voltage here is V out over R2 is equals to 0. So we can calculate this to get I1, right? So that means if we're trying to find I1 is equals to negative I2. Is that right? Yes. Okay. So since we are trying to find I1, so what we are going to do is we're going to have 0 minus 5 over R1, which is 1800. And I'll just use my calculator. Minus 5, 1800. Is equals to negative 0.0277, but it's good always to have like in 3 decimal points. So we're going to round this off, and it's going to be negative 0.028. So I1 is equals to negative 0.028, and we can change it into milliamperes. Is always good to do that. So this one in milliamperes, that is just 1. Okay, that's 1, 2, 3. So it's gonna be did you guys didn't round it off? I rounded off into 3 decimal places.
I mean, yeah, we can go.
It's still the same thing though. So it's just gonna be 2 point wait, just a minute.
Where it comes in, it's in 2.77.
Yeah, 2.778.
This is
But
an extra zero.
This one?
Yeah, it should be 0.6.
Oh yeah,
Yeah.
that's sorry. I didn't say that one. Sorry. So this one becomes 2.8 for me, but you can still you can round it off to any decimal point you want to do. It's still gonna give you the same answer. So, but here we have it as 2.78 milliamperes. Okay, so that is I1, right? But according to our golden rule, we saw that I1 is equals to I2, which is equals to 0, right? Which if we do that means if this one is negative, the other one needs to be positive, right? So that is equals to 0. So it's gonna be negative 2.78 milliamperes. And then I2 is gonna be the opposite of this, which is 2.78 milliamperes. So those are our currents. And then we are trying to find I3, right? So I3, we look at this node. We have this node here using KCL, right? Using KCL, we see that this node, this current is coming out of this node, right? And then we see also this current is coming out of this node. And we know KCL is the summation of the currents that come in and out of a node is equals to 0, right? So we know that I2 plus I3, and this one is coming in, I out is coming in the node, is equals to I out. Or we can write it like I out is equals to I2 plus I3, right? So that just tells us that this current added with this current is going to give us the current of I out, right? So we look at I3. Before that, we can also like get the V out, because when we get the V out, it's going to be easier for us. So since this is a non-inverting amplifier, V out is equals to 1 plus R. Am I going fast? Okay. Well, RF over R1 times V in. Okay, so that's just that is just like it's an equation that is already like derived for you. So this is just an equation for a non-inverting amplifier. So V out is equals to 1 plus, I told you as I started that this resistor here is always called RF because we see that the output is going back to the inverting one. It's like a negative feedback. Sorry, I don't know how to explain that one. So we take 4500 over 4500 over R1, which is 1800, and that gives us, using my calculator, 1 plus 4500 over 1800, which gives us 3.5 times V in. Our V in was 5. So times 5, that gives us, I want to be sure, out, it gives us 17.5. Is that correct? Is that what you guys got? 17.5?
Yeah.
Okay. So since we have already gotten our V out, now it's easier for us to calculate the rest of the stuff, right? So I out is equals to, we see I2. So I2 here, we see that the voltage here is Vs minus V out, which is 17.5 over the resistor, which is R2, which is 4,500 ohms, plus I3, which is V out. And then here, the voltage here is 0 because it's connected to the ground. So minus 0 over R3. So this is just Vs is 5 minus 17.5 over 4,500 plus V out. Here we got was 17.5 minus 0 over the R3 is 850. So I'll just use my calculator here. No, sorry. It was the other way around because it's the other way around, sorry. Where's the eraser? It's the other way around because of where the current is going. So sorry, this is 4. So when we do that, we'll get it to be I out is equals to 0.004836. And it's always good to round it up to 3 decimal because it's just easier. So when we change this, when I take that answer times 1,000, we're going to have times 1,000, we're going to have 4.84 milliamperes. Okay. So yeah, so that's how we got our currents. We have to get our I3, that's I out. So we need to get our I3. So to get our I3, since we have this equation, it's easy for us to get our I3, right? So we just take I out minus I2 is equals to I3. You can write it in any way you want, like I3 is equals to I out minus I2. So I3 is equals to, what did we get for our I out? 4.84 milliamperes minus I2, what did we get for I2? 2.78 milliamperes, right? So when we do that, that is gonna have 4.84 minus 2.78. We get 2.06 milliamperes for our I3. So sorry, I'm all over. I3 is 2.06 milliamperes, and then I out is equals to 4.84 milliamperes, and then our I1 is equals to minus 2.78 milliamperes, and then our I2 is equals to 2.78 milliamperes. So those are our answers. Anybody with any question?
Can I see the V out again?
Oh, the V out? Yeah, so V out is equals to, because it's all these formulas are already derived for you, but you can also derive them using KCL if you ever want to. When you get to ENA, they'll teach you how to do that. But for now, it's already derived for you. You don't have to, kill your brain cells on it right now. You can just use it because it's already given to you. So you just have to know which operational amplifier you're using. And then you just say, okay, it's non-inverting. This is how to get V out. This is how to get gain. This is how to get all other stuff. And this operational amplifier is really exciting to know. And as you move along every classes, you will understand why we have the golden rules and why we use them and how to do a lot of stuff with operational amplifiers. Any other question? Anywhere anybody didn't understand so that I can explain? Don't be shy to ask any question. It's good to ask questions so that you can understand, because when you're going to exam, at least you know something. Any other question?
I3.
Mm-hmm.
I had understanding the output of the op amp.
Mhm.
If it feeds back into it, how does it not violate the fact that
I3 is feeding back to where? I don't think I3 is feeding back to anything. I think I3, the other terminal of I3 is connected to ground. Yeah.
So as we go, yeah, sorry.
Yeah.
That's the whole point. That's what it's gonna do.
Yeah. But as you go in deeply, you will understand positive and negative feedback when you're having amplifier and the effects they do to operational amplifier. Because when you have a positive positive feedback, your amplifier is not going to work correctly as you think. So yeah, that's why we kind of use more of negative feedback while doing amplifier. I don't want to talk much about it, so you get confused.
All right. So I'm just going to go through a quick review of the formulas you need to know. So feel free to stop me if you need to write down the stuff. So with inverting, all you need to know is that this input goes to the inverting input. That's what you check for. So once you verify that, this is the formula you need to know. The gain is equal to negative RF over R1. And like we said before, it's already, the most of the hard work has been done for you. You just need to remember the formula for this class. So that's the formula. Be sure to check where the input is going for an inverting amplifier. With a non-inverting one, you have the input going into the non-inverting input, the one with the plus sign. And then your formula for the gain would be 1 plus RF over R1. And just as a general note, gain is equal to V out over V in. So just remember that. But yes, 1 plus RF over R1. A summing amplifier, that's actually more of an extension of the inverting one we covered first. So all your input resistors, they're going to the inverting input, but now instead of just R1, you're going to have multiple. It can be 2, it can be 3, it can be how many. So you're basically summing the input resistors into the inverting input. So that is why we are still keeping the negative sign when calculating Vout, just like for the inverting, but now you're summing the currents from each resistor. And this will be for Vout. So be sure to remember that it's not Vout or Vin, it's Vout. Just keep that in mind. All right. This is usually the one that causes the most confusion, but trust me, it's not as bad. You only have to worry about one case where R1 divided by R2 equals R3 over R4. But the main thing, which you do need to practice it a lot, don't rely on these numbers. They will label this as RF or R1 or R3 or whatever it is. You need to know which is the resistor. So the formula you need to know for this class is your feedback resistor. So in this case, it's R2 divided by one of your inputs, R1, times the difference between the voltages. So try to understand more about the placement. So like just repeating it again, you're taking the feedback, dividing by R1 as the input, and then you multiply it by the difference of the voltages. And you don't have to worry about this for now. Yeah. Yeah, thankfully. So this is just an example of the difference amplifier, just to see how it works. So like what I was saying, they obviously labeled it differently. So don't just go with R2, R1, don't do that. But just to write it down again, this is 1 kilo ohms. That's 1 kilo ohms. R3 is equal to RF. So we need to find what RF is. So using the formula, that will be equal to RF divided by R1 times V2 minus V1. We were given V out as 6 and RF is what we are finding. R1 is 1 kilo ohms. And our V2 and V1, that's 7 volts minus 4 volts. So it's pretty simple. You can solve for RF, so that gives you 2 kilo ohms. So again, the formula is not that bad. It's more about knowing what resistors you can use. So we went RF divided by R1 times the difference between V2 and V1. And with the operation, you are basically doing subtraction with the voltages. And I know it looks more like division, but it's technically multiplication. It's kind of like scaling down. That's why we say multiplication. But the operation are those. Do we have any questions so far over op amps? We're going to be moving on to filters next. All right, cool. We can go through it at the end. So like, let's go through the filters, and then if you, especially if you have a specific example, we can go through it for sure.
Okay. All right. So now, okay, my name's Arman, and now we're basically getting to filters using op amps. So The only difference between a filter and the other op-amp circuits you're seeing is the addition of capacitors, either as the reference or the input. So when we're dealing with filters, we'll see gain used in two different units. We'll see volts over volts. So this is the traditional gain you've seen. Gain equals negative RF over RI. The gain is in units of volts over volts. And what else we'll see is the unit of decibels. So both of these are still related. You can still convert between them. So real quick, I'll just run through some formulas behind all of these. So underneath volts over volts, right? So our passband gain will be, or the absolute value of it, will be RF over RI, RF over RI, as if it was a inverting amplifier. But once again, we're only concerned with the magnitude. That's why there's no negative. And then if you want to convert from your volts and so if you want to convert volts over volts to decibels, then it would be A, which denotes our gain in decibels, 20 times log base 10 of our gain in volts over volts. Oh yeah, for sure. Okay. And for at cutoff frequency, so if we have a specific input frequency, which happens to be a cutoff frequency, that gain, if we want to calculate in volts over volts, so gain at cutoff with the units of volts over volts will be our gain in our passband divided by √2. So that's when you're specifically at the cutoff. Now, if you're working with decibels, well, then your gain in the cutoff in decibel will just be your gain in the passband, and then you subtract it. So these are just some quick formulas which are already given to you. So, okay. Oh yeah, another thing, the attenuation region is basically where the gain starts dropping. So you might have seen a Bode plot like this, right? This scale is log, this is linear. This whole graph is called a semilog graph. And basically the point is, given a specific filter, we want to know the frequency, we want to know the gain at different frequencies. So you'll get something like this, maybe you'll get something like this, or if you have a passband, I believe, you might get something like this, right? So the attenuation region is basically the slope region where stuff starts falling off. So let me give a specific example. If this is a low pass filter, this is the attenuation region. Attenuation region. And basically every decade you increase or decrease from your cutoff frequency, you subtract 20 decibels from your gain. So I can show you guys real quick what an active low pass filter looks like. It looks exactly like a non-inverting amplifier, except now you have a capacitor added as on reference. So you can think of it like this. When your frequency is very low, this impedance is going to be very, very high. And if you combine it in parallel, you get an overall impedance that's very high, right? And when you do that impedance divided by Ri, you'll get some sort of like gain value that'll be high. Actually, I'm sorry. What am I saying? Right. Okay, yeah. Yes, that's correct. Okay, given an active low-pass filter, your cutoff frequency is given by this formula. Your resistance and capacitors comes from this side. And then your gain outside the passband is your impedance, because once again, we're combining parallel capacitance and resistance over your resistance over here. But once we're in the passband, we can approximate. We can assume that capacitor is disconnected, or it's basically not there, that our passband is basically RF over RI. Okay. Let me go to a quick example. Okay. This is a low pass filter. How do we know? Because if we consider our cutoff frequency, right, when it starts falling off, our passband is to the left. That means we're allowing frequencies that are lower through. That's why it's a low pass filter. Real quick, I'll just draw a circuit diagram because it'll help us follow with what's going on. So here's what it will look like. So here's our op amp. Oh. So this will be RI, RF, CF. Okay. All right, so we're given a angular frequency of 6,000 radians per second, a gain in decibels of -1, our reference resistance as 1,300, and our input voltage is 5 volts peak to peak. Okay, so we're asking what is the value of CF? So if you remember back to, it was this one, active low pass filter, right? CF, this is what we need. So if we multiply 2 pi over, this is frequencies in hertz, but when we multiply by 2 pi, we get angular frequency. That's how we get omega C. I'll show that in the formula later as well. We have RF as well. That means we can find this for sure. So let me just put down the formula. So frequency at cutoff equals 1 over 2 pi RF CF, right? If I give you frequency and you multiply by 2 pi, that gives you your angular frequency, right? So if I multiply this by 2 pi, I get angular frequency. So then I'll have omega C equals 1 over RF CF, and then I'll rearrange to find for CF. CF equals 1 over RF omega C, which should be 1 over 1,300 times 6,000, and that should be like 1.2821 times 10 to the -7, right? But they're asking us to solve in nanofarads, so we need to convert this -7 to -9. The way we do that is we want to shift this over twice, which gives us 128.21 times 10 to the -9, which is 128 nanofarads. Or 0.21, sorry. 128.21. 128.21. Okay. All right. Now we want to ask, okay, now they're asking what's the approximate magnitude of the gain in volts over volts in the passband. So if you think back to our formula, our gain in volts over volts equals RF over RI. So, oh, actually, wait, yeah. So we know RF, but we don't know RI. So that means we can't solve for this. So we need to look for another equation. So this is where we use this one. A equals 20 times log base 10 of absolute value of our gain. So we have this gain, or sorry, we have this gain, right, in decibels. So we can solve for this one. So if I rearrange, I get that 10 raised to the A over 20 equals my gain in volts over volts, which is 10 raised to the -1 over 20, which should be 0.89 volts over volts. There we go. Because that's the first two answers. Okay, now we need to find the value of Ri, and we can do that pretty simply, right? Thinking back to our gain equation, gain in volts over volts equals RF over Ri. So we know gain now, right? We just solved for it. We know RF, so we can solve for Ri. So let's do that. So gain in volts over volts times Ri equals RF. So that equals 0.89 times 1,300, which should be, oh wait, sorry, what am I saying? Wait, gain is RF over Ri. Sorry, I solved for the wrong variable. I'm silly. We are looking for Ri. Sorry, we're looking for this. That was my bad. I isolated RF. We're supposed to be looking for this. So I just rearranged it wrong. That's the only difference. We're still using the right formula. So Ri equals RF over gain in volts over volts. So RF is 1,300. Our gain is 0.89. So then we should end up with Ri equals 1458.62 ohms. And I know the answer is 1459.03, but I believe it's within tolerance. So we're chilling. Okay. Now we're asking, what is the approximate gain of the filter in decibels at different angular frequencies? Okay, so this goes back to the attenuation region stuff, right? So we know that our cutoff frequency is 6,000, right? So at 6,000 radians per second, our gain in decibel will just be our gain in our passband minus 3. So our gain in decibel is -1. So -1 minus 3 equals -4. That's how we get this. Okay, now we're asking, what is the frequency at 60 radians per second? And you might think, oh, okay, well, that's 2 decades lower, so I have to subtract 40. But remember, that's 2 decades lower, and this is a low-pass filter. So 60 radians per second is actually within the passband. So that's why our gain will just be -1, because we're in the passband. But now we're at, what is this number? 600,000. 600,000 radians per second. So our cutoff is 6,000, and then we have 2 more zeros, aka 2 more decades. So what we're saying is, here's 6K, and we are all the way here at 600K. So remember, every decade you subtract 20. So what you're doing is your gain in passband minus 20, right, for 1 decade, and then minus 20 again for another decade. So you end up with -1 minus 20 minus 20, which is -41. That's how we get this value. Any questions? Oh, wait, sorry. Okay. Okay. Everyone else good? Okay. Now we get to high-pass filters. The only difference between high-pass and low-pass filters is where the capacitor is placed. And low-pass, it was right over here. It was called CF. Now it's here before our inverting input, and it's called CI. And you can see that the formulas are very similar, right? Instead of being RFCF, it's RICI. And the gain, once again, the passband approximation is just the ratio of the resistors. Okay, so let's go to example problem. All right, here we have a filter. This time we're in hertz. Instead of angular frequency, we're in hertz. 1,000 hertz is our cutoff, gain of 17, Ri is 1,100, and our input voltage is 4 volts peak to peak. So let me just draw a quick diagram to show what we're working with. Oh, wait. Okay, so this is Ri, this is Ci, this is Rf. So what we're asked for is the value of CI in nanofarads. So once again, this goes to the cutoff frequency formula. FC equals 1 over 2 pi RICI. So we know our cutoff frequency, we know our RI value, so we can solve for CI. So if we rearrange, we get that CI equals 1 over 2 pi FC RI. So you get 1 over 2 pi. Our cutoff frequency is 1,000, and then our resistance is 1,100. And that should evaluate to 1.44686 times 10 to the negative 7. So we can rewrite that. Once again, nanofarads is 10 to the negative 9. This is 10 to the negative 7, so we need to shift this over 2. So we get 144.69 if you round. So that's 144.69 nanofarads. So that's our answer for part 1. Or part 1. Okay. Now let's move on to the next question. Was the approximate magnitude of the gain in volts over volts? Okay, so once again, if you go back to that formula, volts over volts, right? We need to find this. We have this, but we don't have this. So you have two unknowns. We can't solve for this. So we need a different equation. That's when we move to that the gain in decibel equation. 20 log base 10 of gain in passband volts over volts. Okay, so I want to solve for this. So I need to isolate. So I get my gain equals, once again, same expression, 10 raised to the A over 20, which is 10 raised to the 17 over 20, which should be roughly 7.08 volts over volts. So this is our answer to part 2. Okay, now we need to solve for RF. So if we use our gain equation, right, gain in volts over volts equals RF over RI, right? So we know this, so we can solve for this. Okay, so RF equals gain volts over volts times RI. So our gain is 7.08 times RI, which is 1100, which should be 7788 ohms. And once again, the answer I input is 7787.4, but it's within tolerance, so we'll be fine. Okay, now we get to gain at different frequencies. So once again, I'll just mark the cutoff frequency. Let's say this is 1,000 hertz, right? Okay, so we're asked, what is the gain at 1,000 hertz? So once again, the gain at the cutoff frequency in decibels will just be your passband gain minus 3. So it'd be 17 minus 3, which is 14. That's how we get 14. Okay, now we're asking for 100 hertz. So this is 1,000 hertz. So 100, I don't know, like let's say it's like right here, right? So we're basically moving down 1 decade. So for each decade you move, you have to subtract 20 from your passband gain. So this will be a passband gain minus 20. So that's 17 minus 20, which gives us negative 3. That's how we get negative 3. Okay, now this one might seem a little tricky because it's like, what is this, 5 times? Yeah, so it's 5 times our cutoff frequency raised to the, basically increased by 2 decades. So we're deep in the passband. But the thing is, we don't need to like subtract 20 because we're in the passband. So our gain will just be whatever's in the passband. So that's why it's useful to sometimes like draw it out and be like, oh, I'm moving right, my passband is to the right, so my gain will just be whatever's in my passband. Okay, any questions? All good? All right. Okay. Next, we're just going to look at bandpass filter, which is a combination of both. So bandpass filter, yeah, it's literally just a combination of both. Here is your low pass, here is your high pass. So in this case, both of the equations will apply. So both of the cutoffs will apply, both of the passband gains will apply, and you'll see that being used in the next problem. So okay, here's our passband gain. Okay, so our frequency cutoff high pass is 2000, right? And our frequency cutoff low pass is 3000. And this makes sense because our high pass has to be lower than our low pass. Here's what I mean. If this is our high pass, right? I'm allowing the frequencies above this. If this is my low pass, I'm allowing frequencies less than this. So I create this central area where there's high gain and everything else is lower. If I were to place it the other way around, then I would get something else. If this was my low pass, then I'm saying here is my pass band. If this is my high pass, here's my pass band. And I get something like this. So that would be wrong because we want to basically consolidate one region. So once again, this is high pass. Okay. We're allowing highers. This is low pass. We're allowing lower frequencies. Okay. We're asked for the value of CI. So once again, let me just draw the actual circuit because it helps keeps track of variables. Okay, so this is RI, CI, RF, CF. Okay. Okay, so here's where we have to be a little careful about our variables, right? We want to find the value of CI, right? CI is before the junction node, which means it's part of the high pass filter. So when we say our frequency cutoff, right? This is going to be high pass instead of low pass. It's not going to be low pass. So we're going to use 2000 instead of 3000 for our formula because that trips people up a lot of the time. So basically our frequency, let me do that. Frequency cutoff high pass equals 1 over 2 pi RICI. Okay, so we're given it in terms of angular frequency, but this is just like regular frequency in hertz. But remember, if you multiply by 2 pi, we get our angular frequency. So even though it might seem like we don't have that variable, we actually do. So okay, let me rearrange. So I get cutoff high pass equals 1 over RI CI, and once again I'm finding for CI, so I'll isolate it. CI equals 1 over our cutoff in the high pass filter times RI. Then this is just plugging in variables. 2000 times what's the RI value? Sorry, 1400. Okay. And when we do that, we should get a value of 3.57142 times 10 to the negative 7, right? And remember, once again, we need this to be 10 to the negative 9 because we wanted nanofarads. So this is 357.14 times 10 to the negative 9, which is basically 357.14 nanofarads. Okay. Now, once again, if this is done, we need to solve for the magnitude of the gain in volts over volts in the pass band. So this just goes back to that gain equation. So gain in your pass band equals 20 times log base 10 of gain in volts over volts. So if I isolate it, once again, same procedure because it's the same formula. 10 raised to the a over 20, which is 10 raised to the 12.5 over 20. And that gives us a gain of 4.22, which is correct. Okay, all right, part 3, what is the value of RF? So now that we have gain, we can use that gain equation. Gain in volts over volts equals RF over RI. So we're solving for RF, so we need to move this over. Okay, so RF. Actually, let me do this down here, just so I save space for something else. So gain volts over volts equals RF over RI. So RI equals, sorry, RI times gain volts equals RF, which equals 1400 times 4.22. 1400 times 4 is 5908, 5908 ohms. So you find that this is actually correct. Okay. Now we need to solve for the value of CF. So CF, the only place this actually shows up is our cutoff frequency equations. So this time we're going to be using CF, which is this capacitor, right? This capacitor is at the top section. That means it's part of a low pass filter. So that means that our cutoff frequency will be our low pass 2 pi RF CF. Okay, so we have our cutoff frequency at low pass. We have resistance, so we can find capacitance. So we find that CF equals 1 over omega C low pass times RF. 3,000 times, should be 5908. 5908, the resistance we just found. That should be 5.642 times 10 to the negative 8, which is 56.42 times 10 to the negative 9, which is 56.42 nanofarads. That's how we find this one. 56.42, which is correct. Okay, now we're just dealing with different frequencies. Okay, so at 3,000 radians per second, what is the gain? So let me label this. This is 2,000. This is 3,000. So at 3,000, we're at one of the cutoff frequencies. This means that our frequency, so our gain here is our gain in the passband minus 3. So that's 12.5 minus 3 equals 9.5. Okay. Now we want to find the cutoff at 200 radians per second. So if you notice, that's a decade lower from 2,000. So we have to subtract 20. So our gain is our gain in passband minus 20. 12.5 minus 20 equals negative 7.5. Okay, now we're looking at 300,000 radians per second. So that's 2 decades higher. So we're like all the way over here, right? So for each decade you move, you subtract 20 from your passband gain, right? Since we're 2 decades over, we subtract 20 twice. So we end up with 12.5 minus 20, which is negative 27.5. Okay, and the final one, we want to find our gain at 2,500 radians per second squared. If you notice, that's between, which is in the passband. So it'll just be the gain in the passband, which will be 12.5. Okay. These problems take forever, but we're finally done. So is there any other questions you guys have about this?
For that, if I can take a photo.
Oh yeah, for sure. Yeah. In fact, we'll post a video as well. But if you want to take a photo right now, I don't mind. Yeah, let me just get everything in there. There you go.
Thank you.
Yeah, of course. Anything else you guys want to like cover, or you guys are confused about any doubts? Okay. Well, in that case, hold on. Okay. I think we're done.
I should have pulled it up. Does anyone have their laptop on them right now?
Yeah.
Go to connect. Yeah, I can type sign that as well.
Is there a specific problem you want to go through, Josh?
Yes, so on the homework, the last one.
It's like a long way. I have to go through like my discrete math to get to it. It's kind of weird. Right
Is
here.
it a connect homework? Like on Mega
Yes,
Hill?
yeah.
Archive
I
class.
don't know where else to have.
Which week? 7, right?
Yes.
7. Okay.
And then go. No, 6 or 7. No.
This one.
Yes. Which is what I just missed. What y'all talking about?
It's fine. We can go through this one too if you want. It's up to you. Do you wanna?
Yeah, because I'm some of these sheets, what always gets me done.
Okay.
So it's the calculation on that.
I see. Okay. Okay, so ZF. Oh, so that's parallel impedance. Okay, that's weird. And then the impedance at, okay. Oh, okay. All right. Should I do it here or should I do it separate?
Whatever.
We can do it here. Yeah, okay.
Oh, wait, are you done with this?
Yeah, we can do it. Yeah. All right. Okay. Should I just draw it? Yeah, I'll just draw it. Okay. Okay, this is a problem for one of the homeworks. Someone had a question about it, so we'll just go through it. Y'all are welcome to stay or leave as you need. RF. CF. And this feeds to the negative input, positive input. Just grounded like that. Okay. And then here are our values. So our voltage source is 5 volts peak to peak. And then our cutoff frequency is 200 nanofarads. Our RF is 20,000 ohms. And then RI is 700 ohms. And then our angular frequency is 100 radians per second. Okay, let's start with part 1. What 1 is asking is, what is the feedback impedance? So ZF equals something with something angle. Okay, so basically what it's asking is, what is the parallel impedance of this? So you guys might have seen this kind of problem before, where you're like, so yeah, it's asking what is the feedback impedance? Feedback implies that we're looking at this right here. Impedance means that it's a combination of resistance and like capacitor inductors. So it would be this. Right? So, okay. So you guys might have seen something like this before. It's just not this specific problem. You might have seen it like this, right? Except obviously there's no inductor. So this is all we're doing. So let's walk through that real quick. I'm going to do it only in variables, and then I'll evaluate the final expression, right? So our ZF, right, is 1 over Z impedance of our resistor plus the impedance of our capacitor to the negative 1. This is just the parallel impedance equation, right? But obviously we need to write out the variables, so I'll do that. The impedance of our resistor is R plus 0J. Impedance of our capacitor is 0 minus J times 1 over omega C. It's all to the negative 1, right? Okay, so we need to flip this, right? But in order to flip this, we need to convert it to polar first, because we can only flip stuff in polar. So this will be square root of R squared plus 0 squared with an angle of 0 over R, right? Okay. Oh, wait, sorry. Okay, and this is in angles, and then I'll do the same thing for the other one. So 1 over square root of 0 squared plus negative 1 over omega C squared. Basically, what you're doing is you're taking the x and y component, you're ignoring the j, and you're basically finding the hypotenuse. Because, yeah. Yeah, if I draw it out, right, this is the real, this is the imaginary. What I'm saying is if I go out some distance in the real, some distance in the imaginary, I'm finding this. This is our impedance, this is our angle. Okay. All right, so, and this will be arctan of negative 1 over omega C over 0 to negative 1. Okay, so let's start evaluating this. This will just be 1 over R angle inverse tan of 0 is 0, right? And then we end up with 1 over omega C arctan. Now this gets a little weird, right? So let me just draw the graph of arctan, right? The top limit's pi over 2, the bottom limit's negative pi over 2, right? So what we have here is a negative number over 0. But what we're going to do is we're basically going to assume 0 is a very, very small number, right? So basically this means that this is a very, very large negative number. So on the arctan graph, if we move to a very, very large negative number, we approach negative pi over 2. That's why we get negative 90 for our phase shifts on capacitors. So let me just move this out. Does that part make sense to everyone? The capacitor, like phase shift, like why that is? So negative 90, negative 1. Okay. Now, if we flip so x plus, sorry. Theta. If you flip a phasor, it's the same thing as doing 1 over r negative theta. So that's exactly what we're going to do. So we'll have 1 over r with negative 0 degrees, which is once again 0 degrees, plus, and then we end up with omega c. So negative 90 is positive 90 degrees to the negative 1. Okay, let me delete this. Everything making sense so far? Like, do you guys want me to speed up, slow down, or like perfect, or? Okay, all right. Okay, so now from this expression, so I have addition, right? And for that, I need rectangular. So once again, I have to convert back to rectangular. So let's first convert this expression. Let me actually write it in red. Right, let's convert this one. So the real part will be 1 over r cosine 0 degrees plus j 1 over r sine 0 degrees. Okay. And then we'll do the same thing here. So omega c sine of 90 degrees plus j omega c. Oh, sorry, that's supposed to be cosine. Oops. cosine sine of 90 degrees. Okay, so cosine of 0 is 1. So this is 1. Sine of 0 is 0. That cancels. Cosine of 90 is 0. That cancels. Sine of 90 is 1. So our final expression is 1 over r plus j omega c to the negative 1. Right? Okay. Now it gets a little more weird because let me rewrite it. So the negative 1 is basically saying 1 over, right? So once again, we have to flip something, right? In order to flip it, we first need to convert it to polar. So now it gets a little more weird. Now we're like, okay, let's convert to polar again. Remember, the radius is x squared plus y squared, where this is x and this is y. So if I plug it in, I get square root of 1 over r squared plus omega c squared angle of arctan of omega c over 1 over r degrees. So it's starting to look a little complicated, but I can promise you it is not that bad. It's just a bunch of variables going everywhere. Okay. Now remember, if you flip something over 1, that's the same thing as doing 1 over that the radius and then just adding a negative to the angle. So that's what we're going to do. So we end up with our final expression of 1 over square root of 1 plus 1 over r squared, right? I just expanded the square out, plus omega squared c squared, right? And then, oh wait, sorry. What am I doing? 1 over that. And then this is negative arctan of omega c r. Okay. And the final expression, let me plug it in the calculator. So 1 over square root of 1 over so R is RF for us, which is 20,000. 20,000 squared plus, what is our angular frequency? Our angular frequency is 1,000. So 1,000 squared. And then our capacitance, 200 nanofarads. So that's 200 times 10 to the negative 9 squared. Okay. So here, let me plug in the numbers. So we end up with 1 over square root of 1 over 20,000 squared plus 1,000 squared times 200 times 10 to the negative 9 squared. Okay. Theta, okay, negative tan inverse of omega, which is 1,000, times capacitance, which is 200 times 10 to the negative 9, times resistance, which is 20,000. Okay, let me do that as well. Negative arctan of 1,000 times 200 times 10 to the negative 9 times 20. Okay, and we should end up with basically this evaluates to 4,850.712. Let me rewrite that, it looks messy. 4,850.712 with an angle of negative 75.9637. That is our answer for the first part. Okay, the next part is not that bad, I promise. Next part is now we're asking for what is the impedance of our input resistor. So we want to find Zi. If you scroll back to this, right, we're finding the impedance of a resistor, and it's a very simple formula, right? Zi equals something with some angle, right? So Zi is the impedance of our input resistor, which is R plus 0J. You convert that to polar, you get R with an angle of 0. So this will just be R with an angle of 0. And specifically, R is 700. So that's 700 with an angle of 0. Okay. Do you guys want to continue this problem or not? Because there is 3 more parts. The next part is calculate the magnitude of the gain in volts over volts at the given angular frequency, and then find the magnitude of the output voltage, and then what is the cutoff frequency. Is that something you guys want to continue with? I don't mind doing the work, but I just want to ask. So I know like it is almost 8 as well, so. I don't know. I think it might take like a similar amount of time. Yeah. It's up to y'all. Y'all are free to y'all. What's it? Okay, that's fair. But yeah, I guess we're done then.
Will you upload this anywhere?
Yeah, this will be uploaded on that IEEE YouTube channel, right? Yeah. Yeah. But yeah, I think that's it. Right? Yeah, good luck. Let us know if you have any more questions in the tutoring channel for sure. But yeah. Yeah. Okay, Zoom. Okay, Teams.
Quick something you do.
Oh yeah, for sure. It's for the professional development, right? Yeah, got you.